Good day, ladies and gentlemen, and welcome to today's CYP450 Induction Studies, Benefits of an In Vitro Hepatic Model with Functioning Transporters. All lines have been placed in a listen-only mode. You may submit a question during the webinar by typing it into the Q&A box located on the lower left-hand side of your screen. If you should require assistance throughout the conference, please press *0 on your telephone keypad to reach a live operator. At this time, it is my pleasure to turn the floor over to Ron Latham. Sir, the floor is yours.
Hello, everyone. I'd like to welcome you today to the webinar. My name is Ron Latham. I lead the group at Qualis Transporter Solutions that implements our in vitro ADME studies, such as CYP inhibition, induction, and metabolism. At Qualis, we provide in vitro hepatic models to help our clients predict the effect of drugs and other molecules on the human liver. I'm very pleased today that you've joined our webinar, and I'm excited to have you learn more about how transporter-certified human hepatocytes can help with your drug development efforts. And today that will be exemplified by Intercept Pharmaceuticals' development of obeticholic acid. So now it's my privilege to introduce our speakers today. First up, we have Jeffrey Edwards. Jeffrey is the Senior Director of Clinical and Preclinical Pharmacology and DMPK at Intercept Pharmaceuticals Incorporated. He has over 10 years of industrial experience in clinical and preclinical pharmacokinetics and pharmacology. Prior to leading the group at Intercept, he implemented pharmacokinetic and pharmacology research at Arena Pharmaceuticals, followed by Amylin Pharmaceuticals. We've collaborated with Jeffrey on studies that were conducted at our labs at Qualis, and we'll hear a little bit more about that today. Our second speaker today is Andrew Parkinson. Andrew is Chief Executive Officer of XPD Consulting and an adjunct professor of pharmacology and toxicology at the University of Kansas Medical Center. He founded Xenotech in 1994 and ran the company until 2011. He consults for numerous pharmaceutical companies, and we at Qualis have partnered with Andrew on various projects. Our speakers have prepared presentations that will take about 45 minutes. We'd like to leave some time at the end for questions and some discussion. As Jen mentioned, please type your questions into the Q&A box, and I'll direct the questions to Jeffrey or Andrew as necessary. Again, if you have any technical difficulties during the webinar, you can send an email to Graham Dick. You have his contact information on the invitation to the webinar. And so with that, I'd like to introduce Jeffrey and let him give you his presentation.
Hello, this is Jeffrey Edwards, and I lead the clinical and preclinical pharmacology at Intercept Pharmaceuticals. So today I will be discussing my adventures in assessing potential drug-drug interactions during the development program of obeticholic acid. As you might tell by my verbally updated title, this adventure was anything but easy, and the vast majority of the issues came from using hepatocytes as a monolayer system versus a sandwich-cultured configuration. But prior to discussing some of the science behind this, I would like to present my disclosures and disclaimers. Thank you. Obeticholic acid is a potent and selective FXR agonist that is structurally similar to the endogenous ligand for FXR, which is chenodeoxycholic acid. In terms of its structural relationship, obeticholic acid is identical to chenodeoxycholic acid with the exception of an ethyl group in the 6-alpha position, which allots it 100-fold more potency on the FXR receptor. Like bile acids, obeticholic acid is metabolized in the liver and is conjugated to the amino acids glycine and taurine to form glyco-OCA and tara-OCA, and that the two conjugates have similar potency on the FXR agonist. The farnesoid X receptor is a master regulator of bile acids. Upon bonding with an FXR agonist, the farnesoid X receptor forms a heterodimer with a retinoid X receptor and regulates the transcription of genes involved in bile acid homeostasis. These include genes that are responsible for the transport of bile acids out of the hepatocytes, including BCYP and OSP, as well as genes that are involved in the regulation of the de novo synthesis of bile acids via cholesterol transformation. FXR exerts its effects both in the liver and the enterocyte, as presented in this particular slide. In the liver, activation of FXR causes an induction of the transporters BSEP and OST, which transports bile acids out of the liver into the bile ducts and eventually the gallbladder, as well as into the systemic circulation. In addition, FXR activation leads to an increase in the small heterodimer partner, which suppresses the CYP7A1, which is responsible for the bioconversion of cholesterol into bile acids. In the enterocyte, shown on the bottom, FXR activation leads to an increase in the enterokine FGF19. FGF19 is released from the enterocyte and binds to the FGFR4 receptor in the liver, which again suppresses CYP7A1 and the de novo conversion of cholesterol to bile acids. In addition, FXR activation in the enterocyte leads to an increase in the heterotransporter OST alpha beta, as well as an increase in the ileal bile acid binding protein, which are thought to be cytoprotective in the enterocyte to high levels of bile acids. We have done extensive studies, both preclinically and clinically, to characterize the potential of obeticholic acid for drug-drug interactions. Some of the in vitro assessments include using hepatocytes as monolayers, as well as central cultured hepatocytes, which I'll talk more extensively. But in addition, we have also run microsomal and transfected cell lines along with CACO2. During the development program, we have run 5 clinical drug-drug interaction studies where we examined the effect of obeticholic acid on sensitive probe substrates for OATP 1B1, B3, and BCRP using rosuvastatin, CYP1A2 using caffeine, 3A4 for midazolam, 2C9 for warfarin, 2C19 imiprazole, 2D6 using dextromethorphan, and finally assessing PGP using digoxin. Because the interactions typically were trying to assess a potential for either an induction or suppression, the study designs are shown generally in the bottom right-hand corner of this slide. During these assessments, a single dose of the probe substrate, so for example, CYP1A2, we gave caffeine, was given, and blood samples were collected to characterize the PK profile. Then obeticholic acid was given anywhere from 13 to 14 days, and after that, an additional administration of the probe substrate was given and the PK was characterized. We wanted to have at least 14 days of administration of obeticholic acid to ensure that we would have complete induction or suppression during the characterization. Now, during the initial process, I have to be honest, I wasn't here at Intercept, and a lot of this work was done originally, and we were in discussions at the time with Andrew. They had used a monolayer system to look at the effects of obeticholic acid on the major CYP enzyme and drug transporters. What was very interesting to me is that when looking at the cytotoxicity of the hepatocytes, they were seeing hepatotoxicities at concentrations anywhere from 1, 3, and 10 micromolar. And the reason that was a little bit perplexing to me is that I know clinically we were able to achieve plasma concentrations of obeticholic acid without seeing any type of hepatotoxicity. However, what I had learned, especially when talking to quants, was that often in the monolayer configuration, many of the transporters that are expressed are actually not translocated to the membrane collectively. And so in this particular case, they were telling me that the biosalt export pump actually is not functioning and pumping out bile acids out of the cell. This becomes very important because many of the same transporters that are used by bile acids for their ability to get into the hepatocyte and be excreted are the same transporters that obeticholic acid uses. And therefore, what we believed was that there was actually an accumulation of the drug inside the hepatocyte because it was not able to be excreted out. We then moved on and looked at the effects of obeticholic acid in the sandwich cultured hepatocyte system shown on the right-hand side. And what we observed here is that we were able to achieve concentrations of 100 micromolar, 100 times more than what we were able to achieve in the monolayer system, and we didn't see any hepatotoxicity. And the assumption of this is because the sandwich cultured hepatocyte in this configuration allows for the cell-cell contact and the signaling to allow for the BSEP transporter to be translocated to the apical membrane, allowing the drug to be excreted out into the bile duct, and thus not showing the hepatotoxicity that we see before. The ramifications of using the monolayer system was we were seeing a lot of suppression of cytochrome P450s and transporters at the clinical doses, which were also toxic. And therefore, we believe that that was a little bit misleading. So before moving forward with looking or assessing the potential for drug-drug interaction of the major CYPs and transporters, we first wanted to characterize what were the effects of obeticholic acid on FXR in the genes that are involved with bile acid homeostasis. In our first analysis, we gave obeticholic acid up to concentrations of about 3 micromolar, and we gave chenodeoxycholic acid up to concentrations of 100 micromolar. In the top part of the screen, I'm showing you the induction and suppressive effects for CYP7A1 shown on the left-hand side, FGF19 shown in the middle, and the small heterodimer partner shown on the far right. Based on these results, we saw that there was a suppression of CYP7A1, induction of FGF19, and an induction of the small heterodimer partner consistent with FXR activation. More importantly, what we saw was that obeticholic acid was 100-fold more potent than chenodeoxycholic acid, very consistent with our in vitro results. We also looked at the suppression of bile acids in this system from 3 donors that's shown on the bottom middle side. And here we saw anywhere from about a 35% to a 60% suppression of total bile acids consistent with FXR activation. Now that we had felt that we were comfortable with this new system of the sandwich cultured hepatocytes, we then wanted to make a comparison of the results from the clinical drug-drug interaction studies to those of the sandwich cultured hepatocytes. Now, the farnesoid X receptor is a nuclear receptor, and I'm sure like most of us on the phone, we know that nuclear receptors such as CAR and PXR are involved in the regulation of P450s and transporters that are involved with drug metabolism and transport. There is not a tremendous amount of information related to FXR and its effect on cytochrome P450s and the other phase 2 enzymes in terms of their induction and suppression ability, but one such is CYP1A2. CYP1A2 is regulated by the aryl hydrocarbon receptor and requires coactivation with this nuclear translocator here. It has been shown in literature that FXR activation leads to an increase of the small heterodimer partner, which eventually interferes with this interaction between the AHR receptor and the coactivator, and thus could potentially lead to suppression of the CYP1A2. Now, these results are not actually from obeticholic acid, but from other FXR ligands. When we conducted the analysis in the sandwich cultured hepatocytes, we did see a suppression both in terms of the mRNA, which is shown on the bottom left-hand side, as well as in the functionality, which is shown on the top left-hand side. So the in vitro system would suggest perhaps a weak interaction between obeticholic acid and CYP1A2. In our clinical drug-drug interaction studies, we looked at 2 doses, 10 milligrams and 25 milligrams, which are shown on the right-hand side. The blue symbols represent the profile, PK profile of caffeine when it's being administered not in the presence of OCA, and in the presence of OCA with the red triangles. And as you can see, there is a modest increase in the exposure levels of caffeine, which would be consistent with a slight suppression of the CYP1A2 gene. Next, we looked at the effects of FXR on CYP3A4. It has actually been known that FXR suppresses the mRNA levels of CYP3A4 from other FXR ligands in vitro. But interestingly, in these reports, it has actually been shown that the functionality doesn't change very much. When we look at the effects of obeticholic acid on the lower left-hand side, we can see significant suppression of the mRNA for CYP3A4. But consistent with some of the literature reports on the top part, we see that the functionality actually was just decreased quite minimally. And if we compare it to chenodeoxycholic acid, which is shown in black, there actually really wasn't any effect whatsoever. When we conducted our clinical drug-drug interaction study with midazolam, we really didn't see any effect with either the 10 milligram or the 25 milligram doses, which is quite consistent actually with the in vitro results, although it is a little odd that we had such a significant suppression of the mRNA, but no changes in the functionality. But in terms of the functionality in the clinical DDI studies, we didn't see any effect by obeticholic acid of significance. We then looked at the CYP2D6, which was a rather interesting one. In terms of the mRNA, we didn't see any induction or suppressive effect by obeticholic acid. And with chenodeoxycholic acid, there was some variability and looked like there might be a small rise in the mRNA levels. We did not actually assess any functionality in terms of the 2D6 in the in vitro system, but our clinical drug-drug interaction studies were consistent with the mRNA results, where we really didn't show any meaningful change between the PK in the absence and presence of obeticholic acid, either at the 10 or the 25 milligram dose. Finally, when we looked at CYP2C9, looking again only at the mRNA levels, it was kind of variable, but we didn't believe that obeticholic acid or chenodeoxycholic acid was causing any changes in the induction or the suppression of the mRNA. And consistent with this, we didn't see any significant change in the PK profile of S-warfarin, either at the 10 milligram or the 25 milligram dose. We then looked at the effects of obeticholic acid on the transporters BCRP, OATP1B1, and 1B3 in terms of their mRNA. Looking at BCRP at the top, there may have been a slight suppression of the mRNA levels with obeticholic acid and with chenodeoxycholic acid, but there was no clear trends that were observed with OATP1B1 or 1B3. We did see a very modest increase in the exposure levels of rosuvastatin. Rosuvastatin is not specific for any one transporter, but is actually transported by BCRP as well as the OATP1B1 and 1B3. And here we can see that there was a minimal increase in the exposure of rosuvastatin, which may be consistent with the data that we've observed for the mRNA with OCA. Finally, we looked at the effects of CYP2C19. From an mRNA point of view, we didn't really observe anything, either with obeticholic acid or with chenodeoxycholic acid. And in the clinical studies, we did see a minimal change. Primarily, you can see it's occurring early on at the 2-hour time point. And with this minimal change, we're really not sure if it is of any clinical significance. So in conclusion, we had found that the sandwich cultured hepatocyte by far is the most appropriate system to use when characterizing the potential for drug-drug interaction for any molecule that has a steroidal or a bile acid scaffold. We had found that OCA was 100-fold more potent on FXR relative to the endogenous ligand FXR, which is consistent with our in vitro binding results. In terms of bile acid homeostasis, obeticholic acid significantly suppressed CYP7A1, and consistent with the suppression of the de novo synthesis, when we looked at the bile acid levels inside the system, we saw anywhere from a 30 to a 60% suppression. In terms of the in vitro drug-drug interaction evaluation, we saw a modest reduction in CYP1A2, perhaps CYP3A4, and BCRP. However, we saw no meaningful effect on the mRNA levels of 2B6, 2C9, 2C19, 2D6, as well as transporters related to MRP, NDR, OATPs, MATE. In our clinical drug-drug interaction studies, we didn't see any clinically meaningful interactions with CYP3A4, 2D6, PGP, BCRP, OATP1B1, 1B3, although I will say there was a slight increase with it. We did see a reduction in the ability of CYP1A2 to metabolize caffeine, and therefore our USPI actually suggests that you monitor drugs with narrow therapeutic window that are metabolized by CYP1A2, which would include theophylline. And finally, we did see a modest increase in the CYP2C19. However, the clinical significance of this is unknown at this time. Now I'd like to actually turn this over to Andrew, who will talk further and elaborate on the significance of these results.
Oh, I'm on page 20. Sorry about that. Okay, thank you, Jeff. I'm going to introduce the concept of constipated hepatocytes. And this occurred to me as a result of my consulting for Intercept prior to Jeff's arrival. Well, those of you who are in my age bracket will appreciate that from time to time I joke with Yuichi Sugiyama that when he invented all these darn drug transporters, he just made our life a lot more complicated. And I'm pretty sure that Yuichi's comeback would be that he would be very surprised that I've been invited to participate in a webinar talking about transporters, because those of you who know my past know that I'm pretty much a metabolism guy. But I'm here today because I sort of introduced or made the match between Intercept and Qualist. And I'm going to give you some background on how I came to that decision. When we look or consider factors that affect the induction or the suppression of CYP enzymes in cultured human hepatocytes, we might reasonably expect that metabolism and uptake transporters and efflux transporters, all of which are affected by cell culture conditions, might play a role. In terms of metabolism, it's generally played a minor role in CYP induction. We do, of course, pay great attention to metabolism-dependent inhibition of CYP enzymes, but not so much to metabolism-dependent induction. There are examples. If you look at omeprazole, for example, this is commonly used as the positive control for CYP1A induction in human hepatocytes in vitro induction studies. Omeprazole is a sulfoxide, and it's an AHR agonist, hence it's used as a positive control. But omeprazole sulfide, which actually can form non-enzymatically from omeprazole by sulfoxide reduction, is actually an AHR antagonist, and studies out of Patrick Morell's group several years ago showed that omeprazole causes greater CYP1A induction in hepatocytes compared with various cell lines, because in hepatocytes you have CYP3A4, which can convert omeprazole sulfide back to omeprazole, the sulfoxide. And so you lose this antagonist effect. Transporters, uptake transporters, are well known now to play quite an important role in the induction of CYP enzymes in hepatocytes. And for example, rifampin, which is the usual positive control for CYP3A4 induction in hepatocytes, actually doesn't diffuse into cells. It's transported into hepatocytes by OATPs. And the EC50 for CYP3A4 induction in hepatocytes is half a micromolar or less in human hepatocytes, but it's around about 10 micromolar in FA2 and 4 cells. This is a human liver-derived cell line, as shown on the next slide. And so what's the difference? Well, the difference is because FA2 and 4 cells don't express OATPs. And this is shown in this particular publication, where the EC50 for CYP3A4 induction in FA2 and 4 cells, around 8 micromolar, is an order of magnitude greater than that in human hepatocytes. And that's because the FA2 and 4 cells don't express OATPs. And they also don't express CAR, which sort of made these FA2 and 4 cells less than suitable for in vitro enzyme induction studies. Now, efflux transporters can also play an important role in CYP induction or suppression. And as you just heard, this is the case with obeticholic acid, which is transported into and out of hepatocytes. And I came on board because in the first in-house induction study, which actually was conducted by Intercept in Italy, they observed that concentrations of obeticholic acid up to 10 micromolar were not toxic to cultured hepatocytes. This was a single study, and it was followed by outsourcing induction studies to a CRO. And they reported that they were seeing cell toxicity at even sub-micromolar concentrations, very much in the range of plasma Cmax. And in addition to toxicity, they observed marked suppression of CYP1A2 and CYP3A4. again at submicromolar concentrations, which was a clinical concern. And I'd just like to show you the data that was obtained at 1 micromolar of obeticholic acid. You can see from the table that cell toxicity was observed based on 2 measures of cell toxicity, LDH release and MTS, which is a measure of mitochondrial reducing potential. So significant toxicity was observed at 1 micromolar, and this was associated with an 81 to 90% suppression of mRNA, a smaller level of suppression of activity, quite a marked suppression of 2b6, although not quite as great, and an equally marked suppression of CYP450 mRNA, 78 to 99%, and again with less but still significant suppression of CYP450 activity. And I reviewed these studies, and I came to the conclusion with my first reading that this was actually a pretty well-designed induction study. The CRO used 4 preparations of human hepatocytes, 1 to do an initial toxicity assessment, and then 3 for the induction study. They used up to 8 concentrations of OCA, or obeticholic acid, spanning a 300-fold concentration range so that they could measure EC50 and Emax. They looked at CYP3A or CYP mRNA levels and CYP activity, used 2 endpoints of cell toxicity, and they also included studies of the metabolism of obeticholic acid to its glycine and taurine conjugates, which are also FXR agonists. And if anything, the CRO seemed to do more than was necessary, so it wasn't particularly easy to spot what might be accounting for the marked toxicity seen by the CRO versus the single in-house study. So, and this is indicated in what I wrote in my report to Intercept, that with one notable exception, the in vitro enzyme induction study conducted by the CRO, combined with the pharma recommendations in the Chu et al. Paper, a pharma consensus paper with Valerie Chu as the first author, as well as the newer recommendations in the latest FDA guidance. And the notable exception was the length of the adaptation or recovery period. And in Valerie Chu's consensus paper, they say that the most commonly used and recommended experimental protocol for assessing enzyme induction in primary human hepatocytes for regulatory submissions is as follows. And there's a long list, but the first one is that you use fresh or platable cryopreserved hepatocytes as either primary or sandwich culture with a 1 to 2 day recovery period after plating. So I was doing my usual consulting, sat outside relaxing, and all of a sudden it dawned on me that these hepatocytes that were used by the CRO were constipated. And it seemed to me that OCA could probably get into the hepatocytes, but OCA and its glycine and taurine conjugates couldn't get out, hence the cell toxicity. So let me give you a little bit of background on constipated hepatocytes. You may not appreciate this, but hepatocytes are pretty much like conjoined twins. So each cell in a pair can take up drugs, but each cell contributes, and pardon the comparison here, but basically half a bum to make it biocannuliculus. And that's, in my crude opinion, maybe why it's called the cannuliculus. So with these cells, the first step is to digest the liver using collagenase, and with collagenase you can kiss your cannuliculus goodbye. So when hepatocytes are isolated, the biocannuliculi are disrupted, and the cannulicular transporters are then internalized. And consequently, isolated hepatocytes do not express functional efflux transporters, and your efflux port would probably pucker too if you were perfused with the collagenase. So this is not terribly surprising. This was actually discovered by Kim Brower. Her publication is cited at the bottom, and I really would like to have been around when Kim described that to Ken, who at the time, of course, was trying to develop in vitro models using human hepatocytes for biliary secretion studies. Uptake transporters remain intact and functional in isolated and sandwich cultured hepatocytes. But how do you get the efflux transporters to be functional in plated hepatocytes? Well, Qualis has pioneered the use of cultured hepatocytes for in vitro studies of biliary secretion, which obviously require hepatocytes with functional uptake and efflux transporters. And how are these restored? Well, Qualis cultures human hepatocytes in a sandwich configuration with a matrigel overlaid, and it's got patented cell culture medium and for a sufficient time that restores the formation of biocannuliculi between adjacent cells and restores the expression of functional efflux transporters. And these are known as transporter-certified hepatocytes. When I look back, I discovered that the CRO that conducted the outsourced study received hepatocytes that were plated and shipped to them overnight. One of the suppliers ships hepatocytes at ambient temperature. The other supplier ships them on a cold pack, and it seems unlikely that biocannuliculi are restored under these cool temperatures, which are actually intended to render the hepatocytes metabolically quiescent. And at the CRO, the plated hepatocytes were incubated at 37 degrees overnight and then treated with obeticholic acid or known inducers the very next day. And so it seems unlikely that biocannuliculi and efflux transporter function were restored with such short an adaptation period, even though technically it complied with the recommendations in the Pharma Consensus paper. And so the high sensitivity of these hepatocytes to obeticholic acid toxicity suggests that they were efflux, they were uptake competent, but efflux incompetent hepatocytes. In other words, they were constipated. And hepatocytes are just like people. If they're constipated, they're easily irritated. So my consulting advice to Intercept and to all of you listening today is as follows. Don't conduct enzyme induction studies in constipated or efflux impaired hepatocytes. Use transporter certified hepatocytes with regular efflux and uptake transporters, of course. And if in doubt, just place your induction study with Qualis, as I recommended to Intercept. If you don't like the term constipated hepatocytes, feel free to call them father-in-law hepatocytes. If that helps you remember, they're full of and easily irritated. In my opening couple of slides, I sort of downplayed the importance of metabolism in CYP induction, but there is something that you want to keep in mind. I think everyone can appreciate the importance of metabolism in the disposition of drugs that permeate membranes with a high rate of passive diffusion, because without metabolism to polar metabolites, such drugs cannot be efficiently eliminated from the body. But transporters can be important for effluxing, and also these polar metabolites that are formed need to be effluxed out of the cells, and obviously transporters play an important role there. But what about drugs whose disposition in terms of intestinal absorption and hepatic clearance is determined by transporters? You might think that metabolism plays an insignificant role in the disposition of transported drugs. However, drugs that are transported into hepatocytes pose a potential threat of hepatocellular toxicity because the unbound intracellular concentration can be much greater than the unbound extracellular concentration. And it's perhaps for this reason, in order to protect hepatocytes, that some transported drugs, not all of them, but some of them, are actually metabolized much faster than non-transported drugs, as shown below. So all of the drugs in the top are non-transported drugs that are identified as sensitive in vivo probe or now index substrates. and all of the ones at the bottom are OATP transporter substrates that are metabolized by CYP3A4. And you see several of them metabolized much faster than the in vivo CYP3A probe substrates. And so the take-home point is that induction studies should be conducted in metabolism, uptake transporter, and efflux transporter competent human hepatocytes. I can't gauge your reaction to my humor. If any of it did cause offense, my sincere apologies. I lead my life according to a quote by John Cleese of Monty Python fame that an Englishman would rather be considered funny than a great lover. And I assure you, my wife of 41 years assures me that she married me for my sense of humor. And with that, I thank you, and it looks like we have some questions to consider.
Okay, so that concludes the presentation. And right now, Jeffrey and Andrew would be happy to take any questions that you might have. Again, just submit your questions in the Q&A box on your screen, and I'll direct them as necessary. So we have the first question from Pranav. He was asking whether we looked at the 1'-hydroxy and the 4'-hydroxymidazolam. And I can say that at the studies done at the other CROs, I'm not sure what they looked at, but with the studies we do here at Qualis, we look at only the 1'-hydroxymidazolam, and that's generally considered to be a pretty good marker of 3A4 activity. We have another question.
Can I just add something that
Sure, Andrew.
Yeah, the hydroxylated metabolites, in fact, the metabolites, I think, of all the probe substrates were actually studied in the clinical drug interaction studies. And I have to say, I'm not a huge fan of doing that, because there are cases where what happens, you would expect, for example, that if you have inhibition of the metabolism of a probe substrate, you'd have increased exposure to the probe substrate, but decreased exposure to the metabolite formed by that enzyme. But that's not always the case. And so the interpretation of the clinical studies is normally more reliably based on what happens to the parent drug, not what happens to its metabolites.
Okay. Thank you, Andrew. We also have a question by Subramaniam. What are the messenger RNA levels in the controls before the start of the studies? For the studies that we did at QPS, we could find that out. I don't have those handy, and I'm not sure if we are able to get that information from the other CROs. But if you want to follow up with us, you have the contact information from the webinar invitation, and I would be happy to work with you on that to get those levels for you. Sinning asked, did you consider a cocktail DDI study in humans instead of individual substrates for the CYPs? So I guess that would be Jeffrey.
Yeah, so we did consider it. Just so everyone understands, the cocktail method would be to put all the probe substrates in as one administration and then analyze them all at the same time. Being very honest, I was too chicken to do it at the time, so I actually separated them out. But I know folks do use it, so it's not like it's invalid. I just was worried. You know, there's always the question of some sort of unknown or unexpected interaction between the different probe substrates during the assessment.
Yeah, if I can just weigh in there, that in my capacity as a consulting for other companies, I've actually noticed that in the last couple of years, the FDA has been recommending quite strongly the cocktail approach to doing drug interaction studies. And I've seen the results of several of these studies, and I've become quite a fan. The probe substrate, or the index substrates as the FDA now calls them, can be combined, not in every combination. We just don't have the validation data to show that every probe substrate can be combined with every other probe substrate, and not mutually interact, but a large number of them can, and I think this is sort of the way of the future.
Okay, great. Thank you. So the next question is from Lois, and Lois wants to know what the source of the hepatocytes are that were used in the Qualis study. And I can say that we have a few different suppliers, Lois. What we do is we have a set of criteria that the suppliers have to meet, and when they have a particular lot of hepatocytes or several lots that meet our criteria, we'll get some sample vials and we will actually do the transporter certification in-house. And if they pass, then we will put those hepatocytes on reserve, and we will draw from those reserves until we qualify other lots of hepatocytes. So actually, that information for most of the donors that we have right now is on our website at qualis.com. So if you'd like to go there, you'd be able to find out a little bit more about the donor demographics and what lots we have that could be available for sale for anyone who would like to conduct their own studies. So Subramaniam had another question about the CYP messenger RNA suppression and the increase in cytotoxicity. And so I just can't.
I think what they was asking is, was the suppression, when I was discussing it, I think with the monolayer system, we saw the hepatotoxicity occurring pretty early. And I think what they're asking is, did we see the mRNA suppression during the toxicity as well? And Andrew, feel free to jump in on this one, but I believe that is where we started seeing some of this effects, although we were seeing suppression even at some of the lower concentrations in the monolayer system.
Yes, and then of course in the Qualis study, where there was no evidence of any type of cell toxicity at 3 micromolar, and in fact, they went up to 100 micromolar with no evidence of cytotoxicity. There was some suppression of CYP1A2 mRNA, and so this can reasonably be attributed to activation of FSR, then activation of SHIP, and then the interference of SHIP with signaling through AHR, and that probably is something that's also going on to explain the suppression of CYP3A4 activity. It is a little interesting that mRNA was often suppressed more than activity. I don't think anyone's investigated why there is that slight disconnect. You do see that some disconnect in induction studies. So, for example, in the Valerie Chu paper, a positive result, for example, CYP3A4 induction is a 6-fold induction of mRNA, but only a 2-fold induction in activity. So it would appear that with induction and with suppression, mRNA levels can change to a greater degree than the corresponding activity.
Okay, thank you for that. Lois had another question, and this would be to Jeffrey. She wanted to know, in the original in-house study at Intercept, did CYP1A2 suppression occur at 0.1 and 1 micromolar?
It definitely occurred at 1, but the 0.1, it wasn't dramatic, but there was a decrease. And I think this goes back a little bit of equating functionality with mRNA, because if you look at the enzyme activity, we did see a decrease in the functionality of CYP1A2 in the sandwich cultured hepatocytes at both the 0.1 and the 1 micromolar concentrations.
Okay. And Sagnik has a question. Does the passive diffusion remain constant in different hepatocyte configurations? Specifically, he's wondering about the Matrigel overlay.
I think Andrew would be better to answer this one, because I'm
actually wondering if Qualis is better overlaid. There are
Yeah, we just happen to have Ken Brower on the line, who knows a thing or two about this, so he's graciously agreed to chime in and give us some insight into that.
Yeah, so the Matrigel overlay that we use, we overlay that on day 1 and then culture them for 4 days. And it's been demonstrated that when the studies are actually performed, the Matrigel, because you change the media every day, the Matrigel, I akin to it, wearing away, so that after about 24 to 48 hours, there's really not much of a Matrigel barrier left if we try and image the Matrigel on there. So the passive diffusion part is probably, I would say, very equivalent to hepatocytes that haven't been overlaid during the time frame when the study is conducted.
Okay. Great. Thanks, Ken.
I'll weigh in with one thing. A few years ago, Yuichi Sugiyama published a paper, and they compared the expression, actually based on functionality, of uptake transporters in plated human versus rat hepatocytes. And the reason the study sticks in my mind is because the isolated rat and human hepatocytes had a very, very good uptake functionality, consistent with what Kim Brower published around about the same time. And what they noticed was that when they cultured the hepatocytes, uptake transporter activity remained pretty steady in human hepatocytes, but it dropped quite significantly and extensively in rat hepatocytes. So another thing to consider is that, here we're talking about conducting studies in human hepatocytes, but the same concerns about the expression of uptake in efflux transporters applies to doing similar studies in rat hepatocytes. And there, it looks like assumptions about the functionality of uptake transporters may be a concern. It appears to drop over time.
Okay. Thanks, Andrew. Sandhya had a question. Besides OCA and CDCA, have you come across any other kinds of chemical classes where we've seen similar types of phenomenon?
I have, and I pay particular attention now to cell culture conditions when I'm asked to consult for drugs where transporters play an important role, because if transporters are getting the drug into the hepatocyte, and especially if the drug is being effluxed into bile, then I pay very, very careful attention. Were the hepatocytes overlaid with Matrigel? Were they adapted to cell culture conditions for sufficient length of time to allow for the re-expression of efflux transporters? And so yes, and it seems to me that more and more drugs are falling into this class. We're not paying any attention to the rule of 5 that Lipinski came up with. So we're not all bent on developing highly permeable drugs. It seems more and more of them are transporter substrates, and so anytime I see a drug with physical chemical properties that suggest it's going to be transported, I pay very, very careful attention to the Matrigel overlay and the length of time of the adaptation period to make sure that the studies are being done in transporter competent hepatocytes.
Okay, thank you very much, Andrew. So Faraz has a question. Are there any studies in the expression of efflux transporters over time with or without Matrigel overlay? And also, what do the efflux transporters look like with overnight adaptation versus 2 days as recommended by Chu et al.? So I think for that one we'll have Ken weigh in.
Okay, so there's a large body of work, majority of it out of UNC by Dr. Kim Brower and her graduate students, but looking at the effects of different culture conditions on expression and function of transporters. The most important point is that you need to have the matrigel overlay to repolarize the system. And without that, you can detect the transporters there, but they're not localized on the correct domain, because without the matrigel, there is no canalicular domain that forms for that. So the matrigel overlay causes the hepatocyte to repolarize. There was some very nice work done to show that, using MRP2 as an example, that over days in culture, after the overlay, that transporter becomes reglycosylated and then moves to the membrane and becomes active.
Okay, Ken, thank you for that. We have a question for Andrew on what % of your clients that you consult for perform induction studies in monolayers versus sandwich culture format?
I don't know that off the top of my head. I think the trend that concerns me the most is that after 2012, when the EMA and the FDA sort of indicated they would prefer induction assessment to be based on changes in mRNA level rather than enzyme activity, it became sort of justifiable to do a 2-day treatment, because whereas it takes about 3 days to get maximum enzyme activity induction, you can pretty much max out mRNA induction after 2 days. And then all of a sudden, it became possible to do an induction study in a working week. Any of you who haven't actually performed an induction study the old way will be struck by the fact that somebody has to come in on the weekend to participate in the study. So I think the trend has been we do a 2-day treatment period, and now if we shorten the adaptation period, we can be done with the whole thing. We can be plating on Monday and have the whole thing wrapped up by Friday. So my particular obsession when I review or plan an induction study is to have an appropriate adaptation period with a matrigel overlay so that we stand a good chance of having functional efflux transports.
Okay. So Kuno has a question. Are the transporter characterized hepatocytes also competent enough for metabolic enzymes and vice versa? I think we'll give that one to Ken.
So my standard statement on there is that they have enough, for what we've looked at, they have significant metabolic capacity to produce most hydroxylated or P450 generated metabolites. I wouldn't claim that they're as active as microsomes or even freshly isolated hepatocytes. That depends a lot. The glucuronide conjugation pathways and the sulfation pathways are very active and equivalent. I would say the P450 pathways are less, but they're still all functional.
Okay, great.
Yeah, I think actually this is one of the nice things about measuring enzyme activity in the hepatocytes, because when you measure mRNA, it's normally a ratio, so you really don't measure the absolute level of mRNA levels in, for example, the control hepatocytes. When you measure activity, you can relate that back to the activity for example, in suspended hepatocytes. So based on the activity measurements, you can get a good assessment. One of the indirect ways to know if your hepatocytes are somewhat normal, ironically, is based on the magnitude of induction. And anytime I see more than a 20-fold induction of CYP activity, especially for 3A4, that basically tells me that those hepatocytes had very low, abnormally low CYP3A4 activity to begin with. That's where that 20-fold induction is, or more than 20-fold induction is coming from. And that's actually kind of a hard message when you're a CRO to develop, to pass on to clients, because they tend to think more is better, but actually moderate increases in activity tend to be a good indicator that your cultured hepatocytes had good functional CYP activity to begin with.
Yeah. Okay, and we also have a question about basolateral efflux transporters, OST alpha and beta, in the monolayer.
So we haven't done a lot of work in monolayer regarding expression of OST alpha and beta. This is Ken. We have done that in sandwich cultured hepatocytes, and there are several publications that will be coming out, or some that are out and more that are coming. We do know that under what I'll call normal conditions, there's low function. The function of OST alpha and beta for basolateral efflux is relatively low compared to the induced state when you add bile acids to the hepatocyte for that, or have an FXR agonist. We can see that those levels go up quite significantly. We here at Qualis have not yet looked at that in plated hepatocytes.
Okay, thanks, Ken. So with that, I think I will close the webinar for today. I want to thank Jeffrey and Andrew for spending time with us today. We appreciate all the information you shared with us, as well as your insightful comments. I would urge anyone who would like more information or has any other questions to visit our website at qualis.com. There you can learn more about our transporter-certified hepatocytes, and you can learn more about what kind of services we offer and how we can help you in your development efforts. So there will also be a video of the webinar posted on that website, qualis.com. So you can view that at any time or share that with anyone who wasn't able to be here today. And we will also follow up with people and send a link. Anyone who is invited, we'll send a link to the webinar so that you have that. So with that, I'd like to thank everyone for joining us today, and I hope you found the information useful, and I hope that you'll visit us on our website and learn more about what we can do for you. Thank you.
Thank you, everyone.